Today, let's try to solve this problem called painting the walls. This one is actually a hard problem, but in my opinion, it's not that horrible. So back to the problem description. In this problem, basically you are given a wall which has size n, and each wall has a corresponding cost and a corresponding time. So if you take a look at the example, this 1 and 1 basically means the first wall, to paint the first wall, you need to cost 1 unit of money and takes 1 unit of time to paint the first wall. And this one, the third wall, is going to take 3 units of money and takes 3 units of time to paint the third wall. So that is the cost and the time for the paid painter. However, there's a trick here when there's also a free painter that it can paint any wall in 1 unit of time of cost 0. And the other tricky part is that the free painter can only be used if the paid painter is already occupied. So in here, let's look at the first example. Okay, so in the first example, the cost is 1, 2, 3, 1, and the time is 1, 2, 3, 2, and the answer is 3. Why? Because there's one arrangement. We're gonna let the paid painter paint the 0 and 1 indexed. So 0 and 1 index, these two, will be our cost. And we will take the free time of this here. I mean, by free time, I mean 1 plus 2 is the time that the free painter can use. So the answer is 3 here because 1 plus 2 is 3. So we're gonna have to pay the paid painter for $3. And then for the remaining part here, and we're just going to use the free painter to paint the remaining wall. So that's the lowest cost that we can spend. And basically there's like a couple more examples to show. So let's take a look at the second example. The second example is 2, 3, 4, 2, and the time is 1, 1, 1, 1. So the answer here is 4. So basically the optimal arrangement here, they said, is 0 and 3 will be painted by the paid painter. So basically it's this one and this one. 0 and 3, sorry, is this one and then the last one. So after painting these two, we kind of gain this 2 time as well. So we can use the 2 time 1 plus 1 here to fulfill, or sorry, to kind of use the free painter to paint the middle walls. So that's why the answer is only 2 plus 2 equals 4. And we can easily see that it is the optimal because if we just choose one cost of the wall is not going to be enough time for the free painter to paint the remaining because all the time is 1. So that's why we at least have to pick 2. And 2 is basically the minimum 2 of the whole cost. So that's why 4 is kind of the minimum that we can get. But this is just, I am reasoning from my naked eye. how can we kind of come up with a solution intuitively? So let's think about it. So let's try to solve this problem together. So the first thought is that, isn't it always better to let the free painter to do the expensive job so we can try to do it greedily? No, let's take a look at this example actually. So we're given an array, which I'm going to just assume this is a wall with 4 sides. There is 4 walls. So the first wall with a cost 100 and the time is 3, and the second wall with a cost of 99, the time is 1, and the third wall with a cost of 98 and the time is 1, and a fourth wall with a cost of 97, the time is 1 as well. So here, if we are going to let the free painter do the expensive job, then probably we will end up picking this 97. And then we're also picking this 98. And then we'll let the free painter do the remaining. So we'll have something like 98 plus 97 as the answer. However, if we just take the first job, even though it's more expensive, but it has more time for us to do, for the free painters to work with. So what I'm trying to say is that if you first just pay the painter for $100 and then let him work for 3 unit of times, then in that 3 unit of times, we can ask the free painters to paint the second wall, third wall, and the fourth wall. So essentially, we just have to pay 100, which is less than what we do greedily here, which is 98 plus 97. So it seems like trying to optimize with the cost doesn't work. Okay, so what about trying to let the free painter to do the less time consuming jobs? So basically we will just let the paid painter to do the more time consuming jobs first, because when we have more time that the paid painter is working, then we have more the occupied time that we can ask the free painter to do the stuff. So that sounds like an acceptable approach, but no. Let's take a look at the example. So this time the first wall is cost 100, the time is 3, and the second wall is cost 99 and the time is 1. So if we go with the route of optimizing more time to let the paid painter work, then you would end up choosing the first wall for the paid painter. So the cost eventually will be 100. But the optimal answer here, as you can see, if we just pick the second wall for our paid painter, and the paid painter will just do his job and for 1 unit of time, and in that 1 unit of time, we can ask the free painter to kind of paint the first wall. So essentially, we just have to pay $99. So that's why this kind of greedy approach does not work again. So how do we actually solve it? It seems like no matter what we do, there is something that is not obvious to see a greedy approach. So probably in this case, instead of thinking how to do it greedily, because usually in interview setting, they don't expect you to come up with a greedy approach, because even if you come up with a greedy approach, you will have a really hard time trying to prove your correctness of your code. So how about we try to just brute force our solution? If we want to brute force the solution, it's usually very helpful to think about what options we have every time. So in this case, we are looking at all the walls that we choose the paid painter to paint. So for each wall, you can basically have two options, right? For each wall, you can basically either assign the pay painter to paint it, or you can ask the free painter to paint it. So let me write this A first. So let's think about if we ask the paid painter to paint it, then what happens? Well, if we ask the paid painter to paint it, then obviously by the end of the result, we have to plus the wall cost, the current cost of the wall, because we asked the paid painter to paint it. So this is kind of expected to have to also add that to our total result. So plus wall cost. And also, if we kind of pay the paid painter to paint this particular wall, then we should have some kind of record to tell us that, okay, even though we kind of, for example, even though we kind of pay this one unit of money, but we also gain 1 unit of sort of like a free credit. This free credit can be used for the free painter later. So also we should plus the wall time. And if we choose the free painter, then what we can do, first of all, it is not always possible to choose the free painter because we might not have enough free credit, but we can somehow kind of borrow the credit that we have right now. Basically, our credit can go negative. For example, this wall, we have to consider the possibility that I want to use the free painter on this wall. And I kind of promise that later on, I will kind of add up this free credit by choosing some wall to pay and then gain those free time. So it's basically like borrowing money, but in this scenario, it's borrowing the free credit. So back to the option. If we choose the free, then we don't have to add the wall cost because, I mean, this is free. This is good. So it's just plus 0. But the wall time, we have to minus 1 for the wall time. So that's basically can pretty much tell you what is this data we should focusing on. So because we have to consider every possible wall, whether or not to include it or exclude it, include it or exclude it. So the first state we're going to have, let's say f is the function, is the index fi is actually the indexed, let's say, the current wall that we are interested in. And the second index is actually the free time that we have already accumulated. It means that how much occupied time of the paid painter already have. because we can use that occupied time to ask the free painter to do stuff for us for free. So basically, we'll have two parameters here. So fi is the current index, and time is the free credit time that we can use to ask for the free painter to do stuff. So basically, this is the crust, like the main idea of the solution, and this is how we kind of do the state transition. So after that, we will come up with a solution pretty much like ON square. And let's see how we can actually implement that in code. Let's try to code this up. So first we're going to initialize the length of the cost as the n, and then we're going to also initialize this number as the infinity that we're going to use later. Then we're going to do the recursion stuff, and we're going to add line 5 here to just make sure that we are not kind of repeatedly calculate the same index or free time over and over again. Essentially, this will make a huge improvement, making it the time complexity from exponential to ON square only. So as I mentioned before, this f index is just the wall starting at this index, and then the free time is basically the free time that it has is essentially like the time that the paid painter already occupied. So we can use this kind of free time to ask the free worker to work. So basically, this function will return a minimum cost to paying from ith index all the way to the end, assuming there are free times for the free painter to work. And then first, we're gonna do some base case checking. First, if the index reaching the end, it means there's no more wall remaining for us to paint, then we're gonna return infinity. If we have the free time is still negative, it means that we kind of borrow some free time previously, and hopefully we will kind of pay it back later. But if we actually reach till the end and we are still having some free time in the negative side, so it means that some of the free time are never kind of balanced out. So it means that it's not a valid solution. So it's just gonna return infinity. So that's why it means that we are not considering this as a possible answer. So otherwise, then we just kind of calculate the remaining elements that we have from index all the way to the end. And if the free time is greater or equal to remain, it means that because the free painter is actually very efficient, I'm not sure why it is called free painter, it's actually more efficient than the paid painter. But anyway, so here, because the free painter will only cost 1 unit of time to paint one wall, and we have the free time more or equal than all the remaining number of walls. So it means that we can use the free painter to paint all the remaining walls. So that's why it's just going to return 0 in this case. And we're just going to initialize the cost and time of the current wall. So the first possible route for us is to pay to paint this wall. So if we pay to paint this wall, then we have to add the cost at the end because, well, we pay for it. However, there's one benefit for us is that if we pay to paint this wall, then we actually gain this free time as well. That we can use it later to ask for the free painter to do stuff for us. And index +1 because we have to look at the next wall from here. And the other possible route is to not pay it. It means that the other possible is to ask for the free painter to paint it. So in this case, we don't have to add the cost like we did on line 14, but we do have to free time -1 here. So yeah, and then basically we have to pay, or we have to use the free painter because we have to paint this wall no matter what. And the only two options we have is that we either pay to paint it, or we use the free painter to paint it. In here, we just consider all the possible cases. So that's why we just return a minimum of these two is going to cover all the possible solutions. Basically, we just brute force every possible solution in this case. And then eventually we just return 0, 0. It means that because we start at the index 0, and then initially we have 0 free time, of course, obviously. And that's how we're gonna write the full solution. And as I mentioned before, it is an O(n)² solution. Mainly because the free time will never exceed n, because if we exceed n, then the line 11, the condition in the line 11 will just cache it. So that's why it will be an O(n)² solution. And let's try to run this code. Okay, accepted. Thanks for watching, and I hope this is helpful, and I will see you next time. Bye bye.